Math 1343, Review, Standard Normal Distribution, Z, Video 3, Areas and Probabilities. In a normal distribution curve, not necessarily standard, but it could be, the total area under the curve is exactly 1. This can be shown using calculus. I'm not going to show it to you because this is not a calculus-based statistics class, but I just wanted to show you the picture in Desmos to remind you what we mean. Here's a normal distribution curve. In fact, it's standard because I currently have the mean indicated by M set equal to 0 and the standard deviation indicated by S set equal to 1. If you could measure the area under this curve, which technically goes infinitely in both directions, but the curve asymptotically approaches the x-axis, meaning that it gets closer and closer and arbitrarily closer the further out that you go. But if you were to calculate the area underneath that curve, and it would require calculus, then the area would equal 1. And it wouldn't matter if I changed the standard deviation, made it smaller, hence a tighter, taller curve, or move the mean left or right. No matter how I change the parameters, how I change the mean and the standard deviation, the area under that curve will always equal 1. As a percent, that translates to 100%. So what does that have to do with anything? Well, that means we can interpret the area under the curve as a probability, depending upon which part of the curve we're looking at. So the area under a part of the curve is associated with a probability. We're going to look at 3 specific scenarios right now. Number 1, the area to the left of x equals a equals the probability x is less than a. In other words, equals, well, using the symbolic notation, the probability x is less than a. Now, I do have to admit that for the students of mine who took Statistics 1 at UT Tyler, there's a good chance you didn't talk about probability. Usually probability is a key part of Statistics 1. So if this is new to you, don't let it bother you too much. All you need to know is that the probability of an event is the likelihood that it occurs. If an event must occur, then there's 100% probability. For example, the probability that my name is Chris is 100%. As opposed to if something can't occur, its probability is 0. The probability that I'm 10 feet tall is 0. Anywhere in between means something can happen with a certain likelihood. Obviously, the closer to 100% of probability, the more likely it is to happen. But what does that mean in the context of bell curves and whatnot? If you have a continuous quantitative random variable with a normal distribution, with a certain mean and a certain standard deviation, and you pick a value at random from that data set, then the probability that you are less than a certain value is equal to an area. Here's the picture I want to draw, not that, but this. If we have some bell curve with some mean, so we'll just stick mu in the middle, and we pick some value a, let's put it over here just for the sake of discussion. And we somehow, let's see, I think I can do this. That's not what I want. I want this. There we go. We can, and if somehow we could find this area, how much area is underneath this curve? Give me 1 second to shade it in. I think my stylus accidentally came off the screen. Yeah, I can tell because of the dark overlap in the middle. But if you could shade that in and calculate its area, then the probability that you pick a number in this distribution and it's less than whatever that A is equal to that left area. So left area tells you probability that you are less than a certain number. Now, vice versa, the area to the right of x equals a equals the probability x is greater than a. So if we were to draw, let's move that up a little bit. If we were to draw some normal distribution with its mean in the middle. And notice I'm not indicating the mean because the mean really doesn't matter. And you pick any number on this number line. Let's just say we pick it over here just to be different. It really doesn't matter where it is. And we shade in everything to the right of that. We'll shade this one in orange. I'll try not to pick up my stylus this time so that it doesn't have any dark spots when I let go. And I'm not going to fill it in completely as I'm trying to fill it in completely. I think that's good. Notice it's monotone now. But if you have a value on your axis, doesn't matter where it is, left of center, right of center, it could be in the center, and you know the area to the right, then the probability, let's put this in black, the probability that a randomly selected value is greater than whatever that A is or whatever you're calling it is equal to the right area. So in a normal distribution curve, really in any distribution curve, but in this case, in a normal distribution curve, the area to the right of a value is the probability that if you pick a number at random, it will be greater than that value. Left area is probability of being less than. Notice the alliteration. Right area is the probability of being greater than. There's a third variation on this theme. The area between two numbers, x equals a and x equals b, equals the probability x is between a and b. So now if I pick two numbers, and I didn't state it in this example, but we're assuming a is less than b, so a would be to the left of b. And I'm not going to bother marking the middle right now, but I will try to draw these lines a little bit better. Wherever the middle is, it's the mean. But if we have two values and it cuts off a middle area, we'll label this one blue. There we go. Okay, so I didn't stay in the lines, sue me. Then that area tells us the probability that A is less than X is less than B. In other words, if we pick some random number, then the probability it's going to be between whatever A and B is going to be this middle area. So from a visual perspective, that's what areas under bell curves mean. Left areas give you the probability that you are less than a value, whatever the boundary is separating that left area. Right areas tell you the probability that you're greater than a certain value. Middle areas tell you the probability that you're between two values. One last comment. In all of these cases, you can use greater than or equal to and less than or equal to. In other words, if I were to draw this picture, let's put some specific values. Let's say we have a mean of 10, but we're looking back over here at 8, and we shade in everything to the left of that. Then let's just say for the sake of discussion that this area, I don't know what this area is. All that I know is that it's less than a half. It should be pretty evident that half of the area is to the left of the center, half of the area is to the right of the center. I didn't quite shade everything to the left of the center, so it's got to be less than 1/2. But let's just say for the sake of discussion that this area is equal to 0.35, or as a percent, 35%. Then we could say that the probability that x is less than 8 is 0.35, or 35%. But we could also say the probability x is less than or equal to 8 is 0.35. So that's one of the nice things about these areas under bell curves interpreted as areas. It doesn't matter if your inequality is strict or allows the possibility of being equal. In the next video, we'll talk about the z-distribution chart and how it's used to calculate areas and hence probabilities.